Welcome student to the next class of Introduction to Nonlinear Optics and its application. So, in the previous classes we have find a very important concept about the susceptibility and specially how it relates with the frequency, and then find out one important law which is called the Miller's rule, where we can find the susceptibility of different frequency and can correlate them with a particular frequency. So, now today let us see what we have in our class. So, today we will have three very important concepts in nonlinear optics. One is linear and nonlinear polarization. The first one we will going to learn what is the meaning of linear and nonlinear polarization. However, this term has already been introduced to you, that is nothing new, but we will going to learn in detail. Then the dimensions of higher order susceptibility. So, susceptibility in general is a quantity which has some kind of dimension. So, we will find out what will be the dimension of the susceptibility when it is higher order. And then very important concept, second harmonic generation. So, second harmonic generation is one of the important concept as we learned from the previous courses or previous classes, that when we launch a particular frequency and if it is passed through a nonlinear medium, then what happened that this frequency get doubled. So, we will get a frequency having twice than the input frequency, and this is generally called the second harmonic generation. So, today we will going to learn how this second harmonic generation is there from the very first principle calculation or very simple calculation. Okay. So, first polarization is different form. So, if I look this slide, then you will find there are three forms written here. One is in vector form, that is the first one, this is in the vector form, and then one is a component form, and then in a scalar form. In the books, if you find any nonlinear optics book, you will find that the polarization is always defined by these three forms. Either it is in vector form, that is the first one, or it is in component form, that is the second one, and or it is in the third form, like the scalar form, we called it the scalar form. So, every form has their own significance. So, let us try to understand three different form in a more detailed way. So, in the first form you can see that the left hand side is a vector quantity. So, P is essentially a vector which is related to the susceptibility tensors, where these quantities are first order, second order tensor and so on, and then it is related to the electric field E. The first term is a well known term, P is equal to epsilon 0 chi 1 E, but the second, third, fourth, fifth etc. terms are written in a different way. You can see that one term is written as EE. This is nothing like a multiplication of two vector, rather this is a notation, this is a tensor kind of notation. This product is not dot or cross product. I just write EE to ensure that the entire thing become a vector, but this product may be related to some tensor property, because these quantities are tensor. So, in order to understand that polarization is a vector quantity, we need to use this particular form in more realistic representation. So, if I say polarization, that means that the left hand side polarization P is a vector quantity. If it is a vector quantity, the right hand side should also be vector, but here these terms are normally tensor. If these are the tensor quantity, then we need to write the E square E cube term in such a way that the entire component should form a vector. So, that is why this is some sort of a form where we can say that the polarization is indeed a vector quantity. So, in order to have the sense that the polarization has some vector property, we normally use this form. So, second form, the component form, are very important, because we are basically representing the first form, but in a more general way, or rather more simple way, so that we can appreciate that this quantity chi is essentially a tensor. So, first here in component wise I write. So, Pi is essentially the ith component of the vector P, and if it is ith component, it should be related to the different component of the E field, because polarization is not only depending on the one particular field component E, but there may be a combination. Since it is E square E cube, these dependence are there. So, if I go to the first term, you can see Pi is related to Ej and chi ij. So, chi ij is nothing but a tensor quantity having few components, and then I is there and j is there. So, there are one j here for this chi and another j is here for E. So, these two j are there. So, we know that this is called the Einstein notation. We know that if the indices are repetitive, then that means essentially we are summing it over. So, that means if I write Pi in a more general way, I should write it as a j epsilon 0 I j and then E j. This I is ith component, but here this j is summation. So, now if there are two components are there j j, which is sitting side by side or repetitive indices, then we should not use this summation sign. So, just reduce the complexity, we just simplify the equation, and this is called the Einstein notation. In the future classes also, we will not going to use this summation sign all the time. Whenever you have these repetitive indices, then you will find you should understand that it is summed over that indices. Okay. So, this is the first term. In the second term, we have chi ijk. When it is ijk, there should be related to j and k, because it is a square term. So, two components should be involved. When two components are there, then there should be ijk. Then the third order effect, where we should have I, j, k and L also, because j, k, L all are there. When j, k, L all are there, then it should be sum over all these indices. So, if I write in terms of summation, this summation is essentially ith component. So, it is j and then k and then L. So, all these things is summed over this, and finally, we have the scalar form. So, scalar form is a most simple form, but it is very useful to understand the fundamental effects. For example, second order effect, third order effect, second harmonic generation, third harmonic generation, sum and different frequency generation, all this important effect can be understood with these terms, where nothing is there, nothing vector component or any vector sign or any component is there, only I am using the amplitude of E. Since we are using the amplitude of E, only the E component is only the amplitude is important, we call it the scalar form, which is very simple and very useful. You can see that the vector sign as well as the ij term is removed here. Okay. After understanding this particular form, that there are three forms, now we go back to our second slide, that we just separate out this polarization into two major parts. One is the linear polarization, where P is proportional to, eventually proportional to the electric field E. In vector form we should have like this, the first term. In vector form, in component form, we have the second, that Pi is epsilon 0 kappa ij ej. This is the normal representation when the polarization is simply linear in nature, and PL stands for the linear polarization, where polarization and electric field are proportional to each other, and P and E are related with this form. So, this is the most standard form we always use for a linear case. However, for nonlinear case, we just change the notation, because in our case the nonlinear polarization is rather important. So, that is why what we do, that we separate out the terms which is related to E square, E cube and so on. So, in vector form again I should write E and so on, this is the vector notation, and I write this is the P nonlinear polarization. Also, the ith component of the nonlinear part of polarization can be represented with these terms, which is the same terms that we have already explained in the previous slide. And finally, PNL. PNL is the nonlinear polarization, and this nonlinear polarization is related to electric field. This is a scalar form. So, that is why E square, E cube are related to that. So, we have 3 different forms here, and these 3 different forms are now divided to linear part and nonlinear part, and in the future classes we will going to use the nonlinear part, and normally we use this component form, which is very useful, and one should understand how things going on. But today, or maybe in the next class, we will be give you more emphasis, we will give more emphasis on into these particular terms or the linear representation, which basically leads to very important outcomes in terms of physics. So, let us now go to our next slide. Okay. In the next slide, what we basically represent is the dimensions of the susceptibility terms. So, optical susceptibility should have some kind of dimension, because the susceptibility is not now first order. In nonlinear optics, we have second and third order susceptibility. So, when the second and third order susceptibility are there, then there is a possibility that it should have some kind of dimension. However, we know that the first order susceptibility should not have any kind of dimension. Why? Because we know that the refractive index is a dimensionless quantity, and refractive index is represented by this term. So, when the refractive index is represented by this term, that means it is one is added with some quantity, which is the first order susceptibility, and this first order susceptibility should be dimensionless, so that the total n, that means the refractive index, should be dimensionless. But what happened when chi 2 and chi 3 are there, one has to investigate. Okay, so let us do that. This is not a very critical thing to understand. So, let us start with the first order polarization or the linear polarization. So, in linear polarization, what happened, that it is related to E, and there is a proportionality relation, and then P is the polarization term, and it should have some dimension, and we know that polarization is a dipole moment per unit volume. Dipole moment is nothing but charge into distance divided by the volume. So, this volume should have 3 distance, that means this centimeter, 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 and this distance is centimeter. So, if I cut, it should be centimeter square, and this charge is coulomb. So, coulomb divided by centimeter square, or in this unit it is a meter square. So, coulomb divided by meter square is essentially the dimension of the polarization. We know the electric field dimension is Newton per coulomb. So, now if I combine these two into this equation, then we can have the dimension of epsilon 0. So, most of you may be aware of the epsilon 0 dimension, but for me, to be very honest, I never remember all this term very clearly. So, that is why I just cross verify and try to find out this dimension in a different way. So, here if we know that this is the dimensionless quantity. So, epsilon 0 dimension can be easily figured out from this equation, from the first equation given in here. This is dimensionless, we know that. I know what is the dimension of E, I know what is the dimension of P. So, once we know the dimension of P and E, if I put that, then the dimension of epsilon will be C0 coulomb square divided by meter square per Newton, as simple as that. Why the dimension of epsilon 0 is important? Because whenever we try to find out, for example, if I try to find out the nonlinear the second order susceptibility, then the P nonlinear is epsilon 0, then chi 2 and then E square. So, epsilon 0 is common both the cases. So, epsilon 0 dimension is important. I try to find out the dimension of this quantity. So, once we know the dimension of epsilon 0, E and P dimension is already written here, then I can readily find out what is the dimension of chi 2. In the same way, I can find out what is the dimension of chi 3 and so on. So, that is why the dimension of epsilon 0 is important. So, epsilon 0 dimension is now known, it is coulomb square divided by meter square Newton. Once it is known, then what we do, we just use that to find out the dimension of chi 2 and higher orders. So, okay. So, here we try to find out, as I mentioned in the previous slide, I like to find out the dimension of chi 2. So, here is my equation. The polarization is epsilon 0 chi 2 E square. This polarization is essentially the nonlinear polarization, but even if it is a nonlinear polarization, the dimension of the polarization, linear polarization and nonlinear polarization should be same, there shouldn't be any difference. So, if I try to find out what is the dimension of chi 2 or the second order susceptibility, then it should be the dimension of polarization divided by the dimension of epsilon 0, which we have already figured out in the previous slide, and then E square of that. So, if I now put term by term, so the dimension of P is coulomb per meter square, that we have already figured out in the previous slide. Epsilon 0 again we are going to use, this is coulomb square divided by meter square and then Newton, and it will be multiplied by the dimension of electric field, which is Newton by Coulomb, and then if I make the square of that, it should be Newton square by Coulomb square, and after combining all these things, finally we have dimension like Coulomb per Newton. So, Coulomb per Newton can easily be represented by meter per volt. This is a more useful unit, and normally we use this unit meter per volt whenever we define the second order susceptibility. But for the students, I give you a simple problem, try to verify that how this Coulomb per Newton becomes meter per volt. So, this is some sort of class work or homework for you to figure it out. So, very easy, you can I believe all of you can do that. Okay. So, after figuring out the dimension of the second order susceptibility, now we go to the next susceptibility, next order susceptibility, that means the third order susceptibility. The procedure is exactly same. So, if I now put third order susceptibility, so my equation is simply P is equal to epsilon 0 chi 3 and then E cube. When we have E cube, the equation is exactly the same, only thing is that in the previous case it was E square, now it should be E cube, other things are almost same. So, now this E cube term I just divided square E, because the dimension of this quantity we have already figured out, and it comes out to be Coulomb per Newton, and then 1 by E is again Coulomb per Newton. So, when we have Coulomb per Newton and Coulomb per Newton, it should be Coulomb square Newton square, and essentially it will be meter square per volt square. So, if I go on doing these things for higher order susceptibility, the kth order susceptibility is simply become meter per volt to the power k minus 1, and then where k is 1, 2, 3, this is a general form. So, this is the way one can easily derive the susceptibility, the unit of the susceptibility, and normally the value of the second order susceptibility is of the order of say 10 to the power minus 20. So, this is a very small value. So, since this order is 10 to the power 20 in terms of meter per volt, normally this meter is not used, normally it is used picometer divided by volt, because the order is so small. So, in case of the chi 3 and all these things also, we will going to measure these things or try to find out what is the value, and you will find that this value is very small. Since the value is very small, normally we use picometer or this kind of units. Okay. Now, the next thing is, if I go back to the slides, our next slides is the second harmonic generation. So, this is a very important concept today we are going to start, that the second harmonic generation is something where if I launch an electric field of a frequency omega, as this animation suggests, that I am launching a light which is red here, and then it is passing through the nonlinear medium where chi 2 is not equal to 0. I am getting two light in the output, one is red and another is blue. Here blue representing the frequency a higher frequency. If this frequency say omega, so this frequency is say 2 omega. If this is red, and if we increase the frequency with a multiplication of 2, then the color of light should change, and eventually we will have a blue light, where the frequency of, we know that the frequency of the blue light is much higher. So, this is just a schematic representation of how the second harmonic generation process is occur, a very simplification or simplified diagram we have, but also we have a experimental figure. So, let me show that the experimental figure. So, yeah, this is the experimental figure. So, in this experimental figure you can appreciate that we have a spot, a reddish spot, which is a fundamental wave or the wave which is launched to the system, and we are getting something which is bluish in nature. So, if this is a fundamental wave, we write is a fundamental, then the other thing is the second harmonic. That means, the frequency is twice than whatever we have. So, now this is the second harmonic generation process. We now need to understand how the second harmonic generation process can be appreciated through our mathematical form. So, the treatment is very straightforward. So, let me give you the idea how one can do. So, electric field E is launched. When the electric field E is launched to the system, because of the nonlinear polarization, we have a representation E square here. So, if the E square term is there, so what will happen? Let us see. So, my total polarization P is epsilon 0 chi E and epsilon 0 chi to E square. Total electric field, I write this electric field as E 0 e to the power I k z minus omega t, a plane wave, plus the complex conjugate of this plane wave. So, that the total electric field become a real one. So, my total electric field E 0 cos k z minus omega t is a real electric field. Now, what we will do, that I will put this electric field, the value of this electric field into the equation. So, when I put this equation, I need to put the value of E square. So, E square I calculate, if my E is E 0 cos k z minus omega t, my E square is E 0 square cos square k z minus omega t. Now, this cos square term we can write in a different way. So, we know that cos square theta, 2 cos square theta is nothing but 1 plus cos 2 theta. So, 1 plus cos 2 theta divided by half is cos square theta. So, I just replace these things here. So, when I replace, I then have two terms, one is half E 0 square and another is half E 0 square multiplied by cos 2 of k z minus omega t. Now, you can appreciate that this 2 term is here. So, this is the frequency omega, and in front of that 2 term is appearing because of the E square term. So, this 2 term basically gives you the second harmonics. So, now when I put this E square to my final mother equation, which is P is equal to epsilon 0 chi 1 E plus epsilon 0 chi 2 E square, then it simply gives you the first term, which is my E, so epsilon 0 chi 1 multiplied by E 0 cos theta, and the second term is whatever we have derived here. So, if I separate out this term and this term, you will find in P there are 3 components are there. One component is having frequency omega, another component where the frequency component omega is not there at all. So, this is a 0 frequency component, and another component where the frequency component is 2 omega. So, these 3 components are containing 3 different frequencies. So, now if I write my polarization P, so this P can be represented in 3 parts, P omega, P 0 and P 2 omega. So, when P omega is there, that means I am talking about this term having the frequency component omega 0, P 0 is here, which gives me no frequency, and another component, this is a constant kind of term. We will going to understand what is the meaning of constant kind of term, and another term which is very important inside the polarization, that this polarization part is vibrating is a frequency 2 omega. So, now here in the right hand side I have listed that which term is giving what. The first term P omega is nothing but the representation of the fundamental wave. The fundamental wave will be represented by this. Second term, which does not contain any kind of frequency, that is why it is written P 0 if you look carefully, it is the optical rectification term. So, this is the average term basically that gives some sort of rectification, it is called the optical rectification, and finally 2 omega. So, this P 2 omega basically generate the second harmonics. So, this is the complete mathematics, which is very simple to understand. Just make E square is cos E 0 cos theta. If I make a square of that and then divide into 2 parts, you will readily find there is a 2 omega term that is appearing inside the P. So, once we have the P, where we have 3 different components. So, see this 2 omega component is represented as a second harmonic. It basically leads to the wave that is now vibrating with a frequency double than the fundamental frequency. Now, let us understand what is the physics behind that. This is a very important thing, and I should emphasize that you should understand carefully. So, what happened? Let us try to understand step by step. I am launching an electric field E with a frequency omega. So, this is my representation of the frequency. So, once we have the representation omega, so that means this is my frequency. So, this E is launched to the system. This system has a nonlinear frequency, nonlinear polarization. So, when we have a nonlinear polarization, the dipole here, this is basically representation of the dipole, this yellow part, this is a dipole, this is a dipole. So, when the dipoles are now going to vibrate inside the medium with different frequencies. So, the vibration of the dipole is basically represented by P. If you remember that P now have 3 components, P omega, P 0 and P 2 omega. So, total P is represented by in this box. So, the first term what happened, that the dipole will vibrate with the frequency omega, because here we have a omega component. When the dipole is vibrating with the frequency omega, it will start, when the polarization is vibrating with the frequency omega, that means the charged particle is vibrating, it will start generating a frequency same as the fundamental one, that is 2 omega. The second part, it should not have any kind of frequency part. So, it will not going to vibrate, but it will going to do something that we will going to discuss in maybe in the next class. But let us go to the last term. The last term we have a frequency component 2 omega, that means the dipole is now going to vibrate with the frequency of 2 omega. When the dipole is vibrating with the frequency 2 omega, it now start generating a corresponding electric field that is having a frequency 2 omega. So, here is a new frequency that will going to generate because of the vibration of the electric vibration of the polarization of the 2 omega. So, now if I now summarize the picture, so these are the total picture. In this total picture, I find that if I launch an electric field, it is passing through a nonlinear material. So, now we have a fundamental wave having a frequency omega, this is fine, but apart from that we have another wave E omega, which is now vibrating with a frequency 2 omega, and this E 2 omega is basically the second harmonic. So, this is basically the second harmonic wave. So, this second harmonic wave is generated because the polarization is now vibrating with a frequency 2 omega. So, this is the physics of second harmonic. Very simply I try to make you understand in a very simple way, putting some diagram so that you can readily understand exactly what is going on. I am launching an electric field. Because of this nonlinear term, we have a E square term here, we call it a nonlinear polarization term, which is depending on E square. And when we put this E square term into the system, we find that there are few terms appearing. One is independent of any frequency, we call this optical rectification term, and most importantly another frequency term is there, which is twice of the fundamental frequency, and that gives rise to second harmonic generation. So, with this note, let me conclude here. In the next class we will learn more about optical rectification and other effects. So, thank you for your attention. See you in the next class.